Everybody, welcome to Chem 1211. I just cut out the answers to test number 1, but this is important stuff I do want to mention. Now, if I were in your shoes, hopefully you have big ones because I have big feet, but anyways, if I were in your shoes, I would be asking now, what grade am I getting in this class? And the answer is simple. It's first of all too early to worry about that, but if you got 90 and above, you're getting an A. 80 to 89, you're getting a B. 70 to 79, you're getting a C. Good news, nobody got below 80. Wow, that made Dr. White so happy. Now, I don't remember what the average is, but it's in the 90s, which makes me so happy. Thank you, and thank you. Now, school's instituting something new this semester, which is what I think of it, but we have to give out quarter semester grades. We've never done that before. I'm going to base that entirely on test number 1. It means nothing. It's too early. There are hundreds of points left to go, but if you did well, that's good. Now, a couple of you had trouble with calculations. I could see by your answers with your calculator. See me after class sometime or in my office hour, and I'll be more than happy to review how to use a calculator. For those who had trouble rounding off, and I know some of you did, again, see me after class or come to my office. Actually, it'd be better come to my office hours, and I'll be more than happy to help you out. My office hours are Monday, Wednesday from 6 to 7:15. If you're working then and need extra help, email me, work out something. All right, any questions so far? I haven't said this in a while, but I think you guys are getting the hang of it. Remember, in my class, there's no such thing as a dumb question. And as one student said to me, and you ask people to ask questions and you answer them too. Yes, I do. That's not the one I want. That's the one I want. All right, thumbs up, people, help me out. You see single, double, and triple on the screen? Thank you. All right, let's go back and review. We're talking about chemical bonds, covalent chemical bonds. That's equal sharing of one or more pairs of electrons. And when we talk about a covalent bond, there are 3 types, and you should know these. Oh no, it's Subtle Tuesday. All right, so the first one is a single bond. And a single bond is which 2 atoms share 1 pair of electrons. Hang in there. Whoever it was, I just hung up on them because I didn't know who it was. They shouldn't have been calling me because they don't know who I am. All right. Yeah, again, single bond. A bond in which 2 atoms share 1 pair of electrons. Double bond. A bond in which 2 atoms share 2 pairs of electrons. Double bond. Triple bond. A bond in which 2 atoms share 3 pairs of electrons. You know something? You know what I feel coming on? It's class participation time. Everybody out loud, but you can keep your mic off. Everybody together with Dr. White. What are the three types of covalent bonds? First one, everyone, single bond. Come on. Everybody, you can keep your mic off, but just say it wherever you are. Second type, double bond. Third type, triple bond. I don't think my voice can get any lower. All right, so remember, a single bond sharing one pair of electrons between two atoms. Like going to first base, a single, one pair. Double bond, sharing two pairs of electrons, like going to second base. We call that in baseball a double. And triple bond, three pairs of electrons being shared between two atoms. Just like in baseball, you go to third base, we call that a triple. I wonder if that's where they got the names from baseball, from chemistry. Nah, probably the other way around. Who knows? All right, we're talking about how we finished up, or we're starting, how to draw the Lewis structures for the following. So let's take a look at this. Let me get to my whiteboard. Everybody see 3 points each on their screen? Uh-oh. Zoom played games with me. Now do you see it? Thank you. Did I tell you I was always the first one down the spelling bee? Keep an eye out. If you see a spelling error, tell me, or just laugh at it hardly. Don't fall off your seat. Now, we did this one before, but let's do it. How do you do the Lewis structure for the following? You look at valence electrons. Nitrogen has 5 valence electrons. Lewis structures are only valence electrons. Therefore, you don't have to do it this way, but I'm showing you the mindset. Remember, put one dot at each side before you balance, double up. This nitrogen says to this one, oh, look, I have 1, 2, 3 unpaired electrons. You have 1, 2, 3 unpaired electrons. Let's share those electrons. And they do. The non-bonding electrons on top are still there. And if we look at each nitrogen, let's look at this one. How many valence electrons does it have, including the shared ones? Let's count. 2, 4, 6, 8. Who do you appreciate, Doctor? No. Uh-oh, bad humor slipped out. But 8, octet. All atoms want an octet because that makes them the most stable. If we look at the other nitrogen, all the electrons, including the shared, 2, 4, 6, 8, 8. So it's got its octet. What kind of bond is between the nitrogen's atoms? And the answer is 3 pair of electrons being shared. That's a triple bond. All right, let me let you try one because I haven't shared all morning yet. That's not right. This is hydrogen cyanide. If you looked at a periodic table, which I don't have open, but I know these by heart, hydrogen is 1 valence electron, carbon is 4 valence electrons, and as you see up above, nitrogen 5 valence electrons. The carbon is in the center. Why don't you draw the Lewis structure for that molecule? Have fun. Go. When you're done, give me a thumbs up or look up and smile. I'll give you 30 more seconds, and then I'll put you out of your agony. Remember, hydrogen's octet is 2. Five, four, three, two, one. Put down your pencils, hand in your test. I'm just practicing. All right, let's do it. How do you draw the Lewis structure for hydrogen cyanide? Hydrogen has 1 valence electron. Carbon, 4. Nitrogen, as you saw above, has 5. Now, carbon is in the center. Carbon looks to hydrogen. Oh, you got 1 electron. I've got 1 electron. Let's share. So as soon as that happens, carbon has 3 unshared electrons. It looks over at the nitrogen atom and says, I've got 3 unshared electrons. You've got 3. Let's share. The non-bonding electrons on top of nitrogen stay there. They don't disappear. Now, let's find out, did we do this right? You never know. And we look and we see Hydrogen has 2 electrons, and that's its octet. Hydrogen is one exception. The octet is 2. Now, if we look at carbon, how many electrons and shared electrons? 2 plus 4, 6, 8. It has its octet. And if we look at nitrogen, it has 2, 4, 6, and 2 up here, 8. It has its octet. Now, I would ask you, and I'll give you 10.2 seconds to figure it out. Name all the covalent bonds in hydrogen cyanide. Time's up. Oh, look, 1 pair of electron, single bond. Oh, look, 3 pair of electrons, triple bond. So in hydrogen cyanide, HCN, there's a single covalent bond and a triple covalent bond. In nitrogen, obviously you saw above, triple bond. Now I have carbon dioxide, and I'll let you figure that out on your own as practice. And I will tell you the carbon's in the center. Looking at my notes for today, important announcement. On Thursday, we'll do chapter 9, parts 1 and 2 problem set. I'll go through Thursday, chapter 9, 1 and 2 problem set. For those who are more visual than auditory, make sure Thursday, before Thursday, you try these on your own. Test number 2 has a lot more material than test 1. Keep up, don't fall behind. All right, everybody see N2, HCN, and CO2 on their screen? Good. Now, I've already talked about this. This screen we can skip. Important valences or vacancies. Again, we can skip this. If you follow how I did, let's share. Now, let's talk about compounds with polyatomic ions. Now, a couple of these I wouldn't put on the test, and so I'll throw that out. And let's look at this. How do we do the Lewis structure for potassium hydroxide? Listen carefully. All alkali metals form only ionic bonds. That means when you see an alkali metal in a compound like potassium, you know it's going to form an ion. What ion? We already did this, so I'll put it down. Potassium forms that. Potassium, let's go back and do this again. And the question would be, draw the Lewis structure. What you change? Uh-oh. There we go. Draw the Lewis structure for potassium hydroxide. How do you do that? Well, potassium has 1 valence electron, oxygen 6 valence electrons, and hydrogen 1 valence electron. Now, as I said, this is going to give up its electron to form this. Now, oxygen has 6 valence electrons, hydrogen has 1. Hydrogen and oxygen say, oh, you've got 1, I've got 1, let's share. If we look over here, hydrogen has its 2 valence electrons, and oxygen, you know, is going to have an 2, 4, 6, 7. Oh, that's not an octet. What do we do? Wait a second. Remember, potassium had a valence electron. And what it does is it gives up its electron to oxygen. So it gets an extra electron. Because this has an extra electron, it has a negative charge. I'm putting the brackets around so you know the negative charge is to oxygen and hydrogen. And this is the Lewis structure for potassium hydroxide. There's 1 ionic bond between potassium and the hydroxide polyatomic ion, and there's 1 covalent bond, and it's a single bond, between oxygen and potassium. Why don't you try this one? Sodium has 1 valence electron, carbon 4 valence electrons, and nitrogen 5 valence electrons. Remember, all alkali metals always form ions. And why don't you try it on your own? This one's a little challenging, so take your time. If you're having problems, you just learn this and I'll show you how to do it. But I thought I'd give you a chance to do one on your own. And I did. And when you're done, thumbs up. All right, let's move on. I think all of you are done. All right, as soon as you see sodium, you know it's always going to be form an ion. And sodium, like potassium and lithium, form a +1. Now, carbon has 4 valence electrons. Nitrogen has 5 valence electrons. Carbon says to nitrogen, I've got 3 unpaired electrons, you've got 3, let's share. And they do. Nitrogen had this one still left over. Now sodium gave up its electron, and where did that electron go? It went to the polyatomic ion. It's called cyanide ion, and it went right here. And now, how do we write this? Remember, this now has a negative charge. You don't put that negative charge, I mark it wrong. And now, if we look at sodium gave up and formed a stable cation, carbon.
Excuse me, we can't see.
You can't see, oh no. I forgot to ask my thumbs up people. Now can you see it? Hold on. Can everybody see it? Yep, thank you, Melissa. And thank you, Vivian, for letting me know. One of the bad things about Zoom when I'm in share mode, I can't see chat unless I specifically open it up. I don't even know if somebody's written something down. That's the bad thing about it. All right, let's go back and do this again. Instant replay. Sodium, 1 valence electron. Carbon, 4. Nitrogen, 5. Look at the top of the periodic table for the numbers there. Sodium, being an alkali metal, gives this up to form a plus charge. Carbon has 3 right here, non-bonding electrons or single electrons. And nitrogen has 5. And if we look, carbon says, I have 1, 2, 3. You have 1, 2, 3. Unpaired, let's share. And they do. Now, when you do that and draw it, you'll see nitrogen has 8, but carbon has 7. That's not an octet. Wait, where did the electron go from the sodium? It went to the polyatomic ion, which I put here, and now it has 8. So this is the structure. Oh no, I went over a minute. It's time for our break. Since I stole the minute from you, we'll come back at 10:51. 10:51. That's on your digital watch, 10:51. I'll see you in 5 minutes. All right, everyone. It's time to start again. Everybody back? All right, let's continue on. All right, can I have everybody's attention? Next couple slides, click, I've turned the switch, we'll be on a test to the off position. I'll start again. Everybody pay attention. Click, I've turned the switch, will this be on a test to the off position? Some stuff I want to cover, but I will never put on a test or a final. All right, now the question is molecules, they have shapes. And Lewis structures show the number and type of bonds, but do not show the shape. And molecules exist in 3 dimensions and have shape, not flat on a piece of paper or your monitor screen. And the shape is determined by valence electrons and the type of bonds. Again, switches off here. And the way chemists determine that is with the VSEPR theory. I'll never ask, and I always forget exactly. I know the theory, but I forget what this stands for, but it stands for valence shell electron pair repulsions. Remember, opposites attract, same repel. Electrons have a negative charge, so they want to be as far away from other pairs of electrons. And this is a way of determining the shape in 3 dimensions of a molecule. And if you have, this should be a capital R, hold on. If you have 2 pair of electrons, it's linear. If you have 3 pair, it's called trigonal. 4 with no bonding electron pairs, non-bonding electron, is tetrahedral. With 1 is trigonal planar, and with 2 is angular. All right, does everybody see some shapes on the screen now? All right, these are 3-dimensional shapes of molecules. And here, the dotted line means this comes toward you, this goes away from you. This is planar. Now, here is trigonal, trigonal bipyramid, and bent. Water, because it has 2 non-bonding non-pair of electrons, 2 bonds, is bent. Carbon with, like in methane, CH4, looks like this. And here's examples of how they look. And they give examples here. And that's about all I'm going to talk about. This will not be on the test. Now, a concept that I will talk about in class more is electronegativity. And it plays an important role in many things. And it's a measure of how the relative attraction that atom has for a shared pair of electrons. When you move from left to right in a periodic table and from bottom to top, atoms are more electronegative. Let's see if I can find my periodic table. It's hiding from me. Hang in there. All right, everybody see the periodic table? Nope. Zoom tells me you should be seeing it. That's what I hate about Zoom. All right, now do you see it? Thank you. All right, let's look at hold on one second. All right, let's look at the periodic table. When you go from left to right, atoms become more electronegative, stronger holding on to electrons. When you go from bottom to top, they become more electronegative. Fluorine is the most electronegative. So if we look here, oxygen's over here, hydrogen's way over here. So oxygen's much stronger. What does this mean? Well, think of two people, it's raining out, and they're sharing an umbrella. And one's bigger and the other's tiny. They share it, but the larger person holds it more over them than the tiny person. So they're not really equally sharing. Don't tell my older sister I told that story, how she got me wet in a rainstorm. She was bigger than me, 7 years older. I got back at her later on. Boy, did I. But anyways, that's how atoms are. Now, what does that mean? You can have, again, switches off, non-polar covalent bonds. That's where there's not equal sharing. I say non-polar covalent, that's equal sharing, and polar where it's not equal. And where's that most important? One of the most important chemicals, if not the most important, probably one of the most, is water. Now, if I draw water like this, and it's bent because of the VSEPR theory, this bond right here is a pair of electrons. Now, oxygen is stronger than hydrogen and says, all right, let's share, just like the umbrella story Dr. White told, but I'm going to hold it closer to me. And it does, and it has a slight negative charge. This is delta. This is capital delta, means difference. Small delta means little difference or slight. And this has a slight positive charge. Same thing happens here. Now, if I take another water molecule, which I have conveniently over here, same thing happens. And opposites attract. This oxygen has a slight negative charge. This hydrogen has a slight positive and a very slight attraction. And this is very important. And you should know this is the one thing I'm turning the switch on. This is called the hydrogen bond. I might have mentioned it before, but I'll mention it again because it's so important. See how important it is? Hint, know this. And that tiny little force, even though it's called a hydrogen bond, it's not truly a chemical bond, but small enough that it holds molecules of water together slightly. How important is that? Well, in here I have a bottle of water. Yep, water. Now, notice it's a liquid. If you look at molecules that are not water, that have the same, and I'll teach you later the concept is called molecular weight, they should have the same boiling point. They don't. Those other molecules are way lower. In this room, at room temperature, they're all gases. That's not a gas. How come this is not a gas? Because of hydrogen bonding. And think about it. On our planet, what if water wasn't a liquid? It was a gas. Would life have formed? Because life first formed in our oceans, liquid water. And if it was a gas, would we have even formed? Think about it, your blood, liquid, mainly water. What if it was a gas? We'd look way different than we do now, if we look at all. So hydrogen bonding, important? Yes. Should you know it? Yes. Question, can I repeat the periodic table? And the answer is yes. All right, when you go from, and if this was not a PDF file, I could write on it, but it is, and it's hard to write on them. When you go from left to right, the electronegativity increases, left to right. When you go from bottom to top, the electronegativity increases. I'll say it again. When you go from left to right, electronegativity increases. When you go bottom to top, fluorine is the most electronegative, oxygen is pretty electronegative, nitrogen is, carbon to some extent, sort of. But these play an important role in our daily life. All you have to do is, it's time for Dr. White to scare all of you. How important? Look at your skin. The electronegativities of certain elements help form our skin the way it is. And what's holding the atoms in your skin together? Yep, they're made of atoms, mostly carbon, hydrogen, oxygen, some nitrogen, a few other things, but those are the key ones. What holds them together? Chemical bonds. And remember, I said the first day, I always laugh when I hear someone say, I hate chemistry. Well, then you must hate the fact that you exist. Because if it wasn't for chemistry, you wouldn't exist. What they're really saying is, I hate whoever taught me chemistry. Which if you ask my older sister, oh, does she? In high school, I was too young to help her. My father did. And to this day, she hates chemistry. I'm an organic chemist, go figure. No, I don't talk chemistry to her ever. Not good. So remember, think of two people sharing an umbrella. Again, don't tell my sister I told you that story. All right, switches off. Polar molecule is a molecule with polar bonds that add together to cancel each other out. There's no dipole moment. And oh no, look what happened. If you look in the lower corner, if I click it right here, we're on page 40 of 40. You know what that means? It's time for a new chapter. New chapter time. It also means, let's see, next Tuesday, we'll do chapter 5 problem set, and then next Thursday, we'll do chapter 10, the one I just finished up. I'll be putting this in an email to you. One of the things I had learned in a course I just finished on how to teach online that the other school required every faculty member to take was that communication has to be a lot more repetitive in an online course, because just because I'm saying it now, if I were in a lecture, you'd hear me. If I'm now, some students might zoom past this on the video. So I'll be putting more things out, emails to you. Yes, you'll have more emails to read, but it'll help you not forget important things, which is a good thing. So it's new chapter time, and we're talking about chapter 6. And we talk about chemical composition. Can I have everybody's attention? Oh, I know how to get it. No, hold on. Everybody's attention. Dr. White likes whistles. Even though I can't find I had a police whistle, I still have a taxi cab whistle. I collected those when I was younger. But anyways, everybody watch. Take a deep breath. Let it out. Take a deep breath. Let it out. Do you feel nice and relaxed? You should. I'm going to be doing some math. Take a deep breath. Let it out. This chapter, we're going to do some algebra. Relax. Take a deep breath. As a student said in one of my ratemyprofessor.coms, you stink at math, don't worry, I'll teach it to you. I don't assume students know things. Therefore, the math will go through. I'll teach you how to do it in case you forgot. Relax. Dr. White will keep you comfortable learning things. All right, let's get back to chemistry and stay relaxed. Now, there's something called the atomic mass and the formula mass. And the atomic mass is defined by definition 1/7 the slides off, 1/12 of the mass of carbon-12, which is exactly 12 atomic mass units. Never use this, don't worry about it. Mass of a sample of atoms is based on the relative abundance of isotopes. I'm going to skip this, and I'm going to skip this too. All right. Switch is on. In fact, if I could only turn it, if I had a dial, like a volume, and you could only turn it to 10, I just turned it to 100. I stole that from the movie Spinal Tap. But anyways, you should watch that movie. Weird, but interesting. All right. Formula mass, also known as molecular weight, which I'll use. And the molecular weight, also called the formula mass, for a compound, that's the sum of all atomic masses of the atoms in a formula. Again, the molecular weight is the sum of all atomic masses of all atoms in a formula. I'll never ask on a test, what's the molecular weight? But I'll expect you to know how to calculate it. All right. Time for a little gift from Dr. White. Are you guys all ready for a little gift from me? Let's take a look at this. Let's go to our periodic table. Now, something I haven't shown you, let me blow this up a little. If you look at hydrogen, and I better ask because, does everybody see the periodic table? Green, you see it? Okay, thank you. All right, if you look at hydrogen, you have the atomic number above in the right-hand corner. Underneath, there's another number, 1.008, and that's the atomic weight of hydrogen. Now, that's based on the abundance of different isotopes on our planet. And I'm not going to go into how do you calculate that, because in the last, I don't know how many decades, I never have had to, so why should you? But you see the number is 1.008. My gift to you is, for this class, use all atomic numbers to 3 significant figures. How do you round off 1.008 to 3 significant figures? Keep the 1, keep the 0, keep the 0, Use 8 to round off. That's not 5 or higher. Drop it. This becomes 101. Let's look at carbon, 12.011. I'll let you round that off to 3 significant figures. Time's up. You're right. It's 12.0. Why don't you try oxygen at 15.999? Round that off to 3 significant figures. Time's up. It's 16.0. Now, do you have to memorize these numbers? No. Do I know most of the ones I use on this periodic table by heart? Yeah, but I've been doing this a few more months, weeks, years, decades than you have. But you'll be given this periodic table. For my test number 2, 3, 4, and the final, underneath your name, it'll say, please use proper significant figures for all calculated answers. And next it will say, please use 3 significant figures for all atomic masses. You're going to find out this makes your life a lot easier on the problem sets and on my tests to round it off. Now, I'll tell you later on, I've used that to do calculations where $200,000 in chemicals have been on the line. If I didn't do the calculation right, I just blew $200,000 of somebody's money. That doesn't happen, because I'll explain how I always double or triple check. But remember, use all atomic masses to 3 significant figures. Let's look what that means. Now, let's find out, how do you calculate the atomic masses of water, ammonia, and sodium hydroxide? Let's go to my whiteboard. Hopefully you all see the whiteboard on there with sodium cyanide. Good. All right. Let's do one, and I'll do one, then I'll let you try. And water. If you look up on the periodic table, notice water has 2 hydrogens, 1 oxygen. What's the atomic weight of hydrogen? What's the atomic weight of oxygen? To 3 significant figures. So what do? You have 2 hydrogens, 1 oxygen. I put the dash there so you know it's not the number 10. Well, this is the molecular weight is the sum of all atomic weights. We got 2 hydrogens, so I got to put 2 times the atomic weight of hydrogen to 3 significant figures. For this, 1 times the atomic weight of oxygen. Do the math. Now you're going to add this together. Am I done? No. Why? Because remember, when you do an addition, you get the same number of significant figures past the decimal as the number that has the lowest significant figures. Remember, you get the same number of significant figures past the decimal as the number you're adding that has the lowest amount. This has 1, this has 2. Quick question, which lower? Time's up, hopefully all pick 1. So now you have to round this off to 1 past the decimal. Keep the 0, use that to round off. Is that 4 or less? And the answer is yes. And you drop that. And the correct answer to this problem is that. 18.0. Let's do another one. And this is ammonia, NH3. Now, the first thing I'd ask you to do is tell me, can you see the periodic table? Everybody see it? All right. First of all of you first find what's the atomic weight, the three significant figures for hydrogen and nitrogen. I'll let you try that out now. All right, hopefully you all did. Watch this. Hydrogen's over here. The number underneath is atomic weight. The three significant figures, that's 1.01. Nitrogen is 14.007. The three significant figures, that's 14.0. And now I'll let you continue calculating what's the molecular weight of ammonia, NH3. And when you're doing this on a test, you can also use your calculator in case you're not good at addition. Remember, when you add, you get the same number of significant figures past the decimal as the number that has the fewest significant figures past the decimal. All right, looks like everybody's done. Let's go do it. All right, question is, determine the molecular weight, which is sometimes called the formula weight that I'll never use. I'll always use molecular weight. That's what I grew up with. And the molecular weight is the sum of all atomic weights. And here we have 3 hydrogen and 1 nitrogen. Each hydrogen is 1.01 atomic weight. Each nitrogen to 14.0. Do the math. Now add it up. And is this correct? And the answer is no. Why? Because you have the same number of significant figures past the decimal as the number that has the fewest. This has 1. This has 2. Which number is lower? Time's up. Hopefully all pick 1. So now you have to round this off 1 past the decimal. Keep the first one. Use that to round off. Is that 4 or less? The answer is yes. I drop it. And the correct answer was the molecular weight of ammonia, 17.0. Oh, let's do one more. Important chemical used a lot in the chemical industry, sodium hydroxide. And it's got 1 sodium, 1 oxygen, 1 hydrogen. Everybody see the periodic table? Why don't you try and find sodium, oxygen, and hydrogen on there and write down the atomic weight. By the way, this one Dr. White knows by heart. There are a few of them I use so often. All right, let's look here. Hydrogen is 1.01. Oxygen is 16.0, the three significant figures. Now sodium, 22.989, round that off to three significant figures, and you get 23.0. Again, this is 23.0, the three significant figures. If you add these all up, what do you get? Is this correct? And the answer is no, because you have the same number of significant figures past the decimal as the number that has the fewest past the decimal. 1, 1, 2. What's the lowest number? Hopefully you picked 1. Keep this, use this to round off. Is that 4 or less? Correct. And the correct answer for what's the molecular weight of sodium hydroxide? 40.0. And that's how you did molecular weight. And we've had our practice time. All right. What we're coming up to this slide, the next couple of slides, in general chemistry is some of the, if not the most important thing I personally know, and I'll be teaching you. At first, it takes a little while to get your hands around it, and I'll be teaching you something to help you that's been my friend for, well, I first learned it, I think 1964 or 65. Wow, I shouldn't have said that. But anyways, don't even add that up. It's too many decades. I'll be teaching you about your good buddy, your good friend, unit analysis. And it's been my good buddy and my good friend for many, many decades. Also, I should warn you, in the next couple of weeks or throughout the rest of the semester, I will be going for the Guinness Book of World Record for saying the most times your good buddy, your good friend, unit analysis. Trust me, you'll be hearing me in your dreams. Oh, I hope not. That'd be scary. All right, let's get into the good stuff. The mole. What is the mole? No, we're not going to talk about a furry little animal that digs holes in the ground. The mole, and you should know this, the mole is the counting unit used by chemists. So the mole is the counting unit used by chemists. And one definition of a mole is 6.02 times 10 to the 23rd things, units. You should know this number is called Avogadro's number in honor of Avogadro, who did some work with gases, I'll explain later, to help define the mole. The actual number was developed by two German chemists who sadly, I don't even know their name, most chemists don't, but all chemists know Avogadro. And 6.02 times 10 to the 23rd. So that's a lot. If I have 6.02 times 10 to the 23rd eggs, boy, do I have a lot of eggs. It's like you say a dozen eggs is 12. Well, chemists say 1 mole. And 1 mole of anything is 6.02 times 10 to the 23rd. When you have nothing better to do, I truly mean nothing better, why don't you try writing that number out with all the zeros? That'd be 6, 2, 0, and 21 more zeros. It's huge. It's time for Dr. White to get personal. It's time for me to tell you what's my all-time favorite birthday gift I'd really like. And my birthday is December, so you got plenty of time. And what would I like for my birthday? A mole of pennies. It's just pennies. I like a mole of pennies. If you do the math, that's 100 million piles, and each pile has $1 billion in pennies. Not a billion pennies, $1 billion. That's probably all the money that has, was, and will be on this planet. But it's just a mole of pennies. So start saving. Dr. White would just like a mole of pennies. It's just a mole of pennies. Pennies, you know, they're little things. So you should know 1 mole is Avogadro's number, 6.02 times 10 to the 23rd. So another way of saying that is 1 mole equals 6.02 times 10 to the 23rd things. And in this class, we'll be talking about atoms and molecules as the things. But remember Dr. White's birthday coming up in December, end of December, and I'd like a mole of pennies. Now, time to teach you an important math concept. Relax. Let's assume I have some relationship A equals B. When that happens, there are 2 ratios you can write. And the first one is A over B. When A equals B, you can write this ratio. And this is not equal, they're separate ratios. And you can write B over A. And this is important to know. See, it says it on the screen, so it must be true. Oh, is that lame? Sorry. But anyway, seriously, if you have 2 things equal each other, then you have 2 ratios, A over B and B over A. Therefore, if 1 mole equals Avogadro's number, 6.02, you can write 2 ratios, this one and this one. And turns out being able to do that is very important and useful. Now, in this class, hold on 1 second, I thought I shut it off and I didn't. There we go. In this class, 1 mole equals Avogadro's number. I'll give you this important information. I used to make students memorize this, but now you should know how to use it. Equals 1 mole of an element equals 6.02 times 10 to the 23rd atoms. 1 mole of a compound equals 6.02 times 10 to the 23rd molecules. Therefore, I have A equals B. I can have 2 ratios. And now, here for that are my 2 ratios. This on top, this on the bottom. This on top, this on the bottom. And those are 2 ratios. As long as you know this, which will be given, and you know you can write 2 ratios, you can generate this. You don't have to memorize this. Ooh, that looks ugly. That's better. So 1 mole equals Avogadro's number, 6.02 times 10 to the 23rd. And if you're talking about elements, it's atoms, because elements exist as atoms, or if you're talking about compounds, you're talking about molecules. So if I have a mole of water, I have 6.02 times 10 to the 23rd molecules of water. If I have a mole of gold, well, that would be nice. I have 6.02 times 10 to the 23rd atoms of gold. Now, it's time for me to teach you unit analysis. Exciting time. I get to teach you, my good buddy, my good friend, unit analysis. And it really does help you on the test. So let's look at this. If this were a word problem on something I might give you, it would be 4 or 5 points. I could even make it 6 points. How many moles of water are in 5.32 times 10 to the third molecules of water? What do I do? Well, the first thing you do is look at what are you being asked? You're being asked how many moles. And sometimes I put the S and sometimes I don't. This question mark tells you that's what I'm being asked to find. What are you given? And it's important you put the units here. We're given this. We have this much molecules of water. So everybody, pay attention. This is how you use your good buddy, your good friend, your analysis. The only thing I have to start with is this number. And it's important you put the units. If I had a magic ratio that I multiplied my starting number by, what, and this is important, units do I want my answer to be in? Moles of water. Now, it's time to use your good buddy, your good friend, your analysis. Whatever units you're trying to get to, go on top of this ratio. Whatever units you're trying to get rid of, go underneath. I'll say it again. Whatever units you're trying to get to, go on top of the ratio. Whatever units you're trying to get rid of, go underneath. Well, I can do that. It's not that hard. So I'm trying to get the moles of water. And I'm trying to get rid of molecules of water. Is there anywhere where I know ratio of moles of water to molecules, some relationship? And the answer is yes. And notice I have here, and this you'll be given in a test, 1 mole of a compound, in this case water, equals Avogadro's number, molecules, and I should just say molecules, and for our case, it'll be water. So 1 mole of a compound equals Avogadro's number, 6.02 times 10 to the 23rd molecules of that compound. So if I have 1 mole of water, how many molecules do I have? Avogadro's number. Now, before I pick up my calculator, I'm going to check, do my units cancel out? And let me remind you, anything divided by itself equals 1. It's gone. It cancels out. So notice here on top, I have molecules of water. Here I have molecules of water. This divided by this becomes the number 1. What am I left with? The units I want. And my good buddy, my good friend, unit analysis helped me. Let me do a better one. Help me come up with the answer. So now I know I'm going to get the right units. So I'm going to do and go to my calculator. One of these days I'll remember to save this and so I can just pop it open, but today wasn't that day. All right. Can everybody see the spreadsheet A1 on the screen? Now could you see it? All right, let's do the math. I'm going to use a spreadsheet, 5.32 times 10 to the 30th divided by Avogadro's number, 6.02 times 10 to the 23rd. And here's the number I want. Now, listen carefully. Avogadro's number, 6.02 times 10 to the 23rd. That's a calculated number. And that is 3 significant figures. 5.32 is 3 significant figures. Therefore, if we look at this, keep the 8, keep the 8, keep the 3. Use that to round off. Is that 4 or less or 5 or higher? Time's up. It's 5 or higher, so I'm going to drop all that. That gets increased by 1, and the answer will be 8.84 times 10 to 6 moles. Does everybody see this again? I saw it decided to burp on me. You get 8.837209 times 10 to the 6th. Round this off to 3 significant figures. 8.83 becomes 8.84 10 to the 6th. Hopefully everybody see the problem on the whiteboard. It's getting pretty full. And therefore, our answer is 8.84 times 10 to the 6th. All right, let me go through this again, because we'll do more of these. Trust me, we'll do more of these, because you're going to get to know your good buddy, your good friend, your analysis. How many moles water are in 5.32 times 10 to the 3rd molecules of water? What are you given? Moles water. All right, what are you trying to find? Moles of water. That's why I put a question mark there. Use your eyes, Dr. White. Thank you. You're welcome. And what are you given? 5.32 times 10 to the 30th molecules of water. Once I do this, I never have to look up here again. Now, the trick to using your good buddy, your good friend, unit analysis is whatever you're given, you start with. You put over here what you're trying to get to unit-wise. You have a ratio. Whatever you're trying to get to, the units go on top of that ratio. Whatever you're trying to get rid of, the units go underneath that ratio. And now we have to find, where can I find a ratio of moles of water to molecules of water? Well, I know 1 mole of a compound equals Avogadro's number of molecules. Therefore, remember, if you have A equals B, you always have 2 ratios, A over B and B over A. In this case, it's A over B. And I put the 1 mole here, 6.02 times 10 to the 23rd molecules of water here. Because 1 mole of water, the compound water, equals Avogadro's number, 6.02 times 10 to the 23rd molecules of water. Remember, anything divided by itself equals number 1. Molecules of water divided by molecules of water cancel out. I'm left with the right units. And now I'll do the math. 3 significant figures, 3, you're done. And that's how you do it. Now, that's the first one. And you may not have gotten it all, but we'll do more. Take a deep breath, relax, and you'll find out your good buddy, your good friend, unit analysis. I'll put that away for a while. Not really. But you'll find out it really is your good buddy, your good friend. Because you don't have to memorize anything. You just have to know how to use your good buddy, your good friend, unit analysis. If I look at the clock, oh no, time flies when we're having fun with chemistry with Dr. White. Now, remember, Thursday, we'll be doing our lab. It's already posted. This is going to be a fun lab because I wrote it, but also it's fun. I mean, it's fun. I wish we were doing it in the lab, fun, but it'll still be fun. And you get to learn a lot too. So don't forget, for Thursday, we'll do the practice problems, Chapter 9, Part 1 and Part 2. Isn't that cool? Part 1 and Part 2. And with that, I'll say goodbye, gang gesund. Bye. I'll see you on Thursday. Be on time. I will. And if you need any help, always feel free to come to my office hours Monday and Wednesday nights, 6 to 7:15. I'll stay later if you need me on Zoom. With that, gang gesund. Goodbye.